So let us start with the concept of virtual memory. These are the points we are discussing. So let us see the need of virtual memory and its basic background. Whenever we write a program, there are so many conditional branchings are there. Say, for example, if the condition is true, call this function, otherwise call some other function, something like that. Or maybe most of the our code is, for example, we open the file. Just example of file opening or file handling. We open the file and then we check if the file successfully opened or not. So if it is not successfully opened, then what to do? So some sort of error handling code is there, or some unusual routines are there, or maybe some sort of large data structures are also there. Say, for example, on separ side we declare some sort of array of size 1000, but we are merely utilizing say 10, 20, 50 elements, 100 elements, something like that. Okay, so not necessarily just instructions, but whatever the data part is also there, right? So we do not require the entire program, or each and every part is rarely used. Okay, so that is the basic idea behind this, which talks about entire program is not needed at the same time. Okay, so at a time we don't need the complete program into the main menu, right? We know that the executable file which is on the hard disk, that needs to be loaded into the memory, but the thing is, do we really need to load complete program into the memory so that it becomes process? So if, for example, 8 KB is the memory requirement, do we need 8 KB at a time? Answer to this question is no, we don't need the entire program, including code and data, at the same time in the memory. Okay, so that means operating system has to provide some sort of ability to execute the partially loaded program. So if 4 KB are there and if page size is say, for example, half KB, total 8 pages are there, maybe I'll load 1 or 2 pages and then I'll start executing. Whenever third page is required, that will be loaded into the memory at runtime, and then we'll continue. So that is the basic idea behind this virtual memory. Okay, this idea actually provides so many advantages. For example, now there is no limit on the size of program based on physical memory. So for example, even though I have just a 2 MB or say 16 MB, or nowadays we have a larger memory in terms of GB, but older systems where we have a lesser memory, the size of my program is limited by the memory. That is not the case with the concept of virtual memory. Okay, and each program takes less memory while running, because we are running it partially. No, we are loading the program partially and we start running. That results into more programs can be loaded maybe partially at the same time. That is what we call is degree of multi-programming. So that results in increased CPU utilization and throughput. Okay, so that results in utilization of processor, and there is no increase in response time or maybe turnaround time. Okay, in addition to that, less IO is needed to load or swap programs into memory, where each user program runs more faster. Okay, so that is basic idea or background behind this virtual memory. Anyways, we'll see how to use it, and what are different ways to implement it. Now we want to separate the user's logical memory from physical memory. Okay, so that is what the virtual memory is there. The key point in the virtual memory is only part of the program needs to be in the memory for execution. No need to load the complete program into the memory. Okay. So whatever my logical address space is there, it can be much larger than the physical address space. That means actual size of process can be more than the size of physical memory available there. Okay. So more efficient process creation, space sharing, multiple programs could be running concurrently. Okay, so all those advantages are there for the virtual memory. Now, what is virtual address space? Virtual address space is logical view of how the process is stored in the memory. So it is just logical view because we simply assume that we are actually making use of physical memory. It is just kind of a simulation kind of a thing. Okay, so that address starts with 0 and it is contiguous address until the end of the space. So it is like address 0, 1, 2, 3, 4 up to you think of any. There is actually no limit for that. Okay. So physical memory is organized in page frames that we already aware. That concept we studied in paging part, where physical memory is organized in frames and logical or this now virtual address space will be divided into pages. And then memory management unit will map the logical address to the physical address. Now you may again get confused between what is logical address and what is virtual address. Both are same. Okay. Only thing is why it is called as a virtual, because previously we simply call it as a logical address that is seen by the processor. But when we talk about virtual address space, this is the logical view actually, and the address starts with 0. Anyways, wherever the process pages are loaded into the frames, that page table that is definitely required, and that will be managed by memory management unit to map the logical address to the physical address. Now, how to implement it? Virtual memory can be implemented via demand paging and demand segmentation. Now, we know the concept of paging and segmentation. Paging and segmentation, that part we have seen. Only thing is one word is added there, that is demand paging and demand segmentation. Demand, meaning of that is whenever that page is required, then and then only load it into the physical memory. It's like on demand loading of page into the memory. That is what the demand paging is there, which is not true in earlier case without the concept of virtual address, because we need to load complete pages into the frames before starting execution of process. That means process needs to be fetched into the memory completely I'm saying. Whereas what happens in case of demand paging is whenever that page is required, then and then only at runtime load the page into the memory. Okay. So whatever the regular normal paging concept we studied, exactly same, like page table is there, the logical address is divided into pages, physical address are divided into frames, the size of page and frame is similar, all that stuff. Now only thing is we need to load it before starting execution of process. All pages here, only required pages will be loaded, and that is what loading of a process partially, not completely, it is partially. Similarly, the segmentation concept we studied, demand segmentation, whenever that segment is required, then and then only load it into the physical memory. That is what the demand segmentation. So there are two ways by which virtual memory can be implemented. Okay, demand paging and demand segmentation. So now here you can see that virtual memory that is larger than the physical memory. So physical memory is there, then Swap space is also there. So this, let me annotate it with, so whatever this one is the swap area. Let me modify it for, okay. This one is the swap. This is physical memory, and this is memory map. Somewhere in between memory map is written there. So this one is memory map, and this memory map is nothing but like your page table or segmentation table. Okay, and now this is the virtual memory. So this is actually larger than whatever your physical memory is there. Okay, so there is no limit for that. Now, virtual address space we need to see. For example, this part we studied, I guess, in very first lecture when we studied about the processes, right? So whatever the address space assigned to your process is actually divided into four. One is code segment where instructions are there, data segment or data part rather, and then heap and stack where there is no fixed boundary between stack and heap, because that is the dynamic requirement of a process. Okay. So they actually grow as per requirement, both heap and stack. The stack is used for function frames. Whenever you are switching from one function to other function, then swap is used. Even local variables are also on the stack. Sorry, not swap, stack. Whereas heap is like dynamic memory required, something like malloc, calloc, whatever the functions you are, where user allocates memory for the program. So that memory will be the heap. Okay. Next one is shared library using virtual memory. So this part actually we have studied, especially when we say shared pages or shared segments. If you remember, I just give an example of editing 3 different data files by the same editor. So we need to load the editor into the memory, and data part is also this. Maybe, for example, files. In that case, whatever the instructions of editor, we are never going to change that. So editor will be loaded only once, but separate data. Now the similar kind of thing is there. Now only thing is it is related to library. So whatever the dynamic link library is there. Now here 2 processes are shown here. So for example, this one is process 1 whose code, data, heap and stack is there, and this is process number 2 whose again code, data, heap and stack is there, and somewhere shared library is mentioned where shared pages will be available. So these shared pages, say for example, you have 2 applications in which you are making use of some sort of mathematical function. Let's for simplicity assume square root function, and square root function is actually implemented from math.h. Okay, so that square root functions implementation will be loaded into the main memory only once, and the same will be accessed by process 1 and process 2. So it is the shared library part of process 1 and process 2. So even though it is required at both the thing, it will be loaded only once. So these are all shared pages. Okay. Now this part is important, that is the concept of demand paging. Okay. Now what happens in case of demand paging? I already mentioned the importance of the word demand, because paging concept we already aware. Okay. So demand paging, it could bring entire process into main memory at load time, or we can bring a page into memory only when it is needed. Now this is the difference between the both. Entire process versus a partial. So whenever the page is referred, then and then only bring that page into the main memory. Why to do so? What is advantage of doing so actually? Advantage is we can have process larger than memory, number 1. Number 2, many processes can be in the main memory, so degree of multiprogramming increases. Number 3, we can provide faster responses because the part of process is already in the memory. Less memory is required. Yes, even more memory is required to load the process completely. We can start executing as soon as desired page is available there. So many advantages are there. Okay. So if you see the diagram where two programs are there, program A, program B, where swap space is also used. So this is demand paging is similar to that swapping. So whenever we do not have space for other processes, we remove that program on the swap storage, and whenever you want to start execution of that, we'll take that pages that is basically called as a swap in. So swap in and swap out. Okay. How to implement it is whenever you do some sort of a reference to it. If it is invalid reference, that means in page table we need to, I think we already studied this part also. Only thing is we studied that in terms of whether that page is part of logical address space of that process or not, right? Whereas what happens here is whenever you load the page into the memory, we'll set some sort of bit. This is a valid page. So valid, invalid kind of a flag will be there. If it is invalid reference, then simply abort it. That means it is not part of now the logical address space of that process. That is one condition. That part we studied earlier. Now, if that page is not in memory, okay, then we need to bring that page into the memory. Once you bring it, then we'll modify its status bit. Now there is concept of lazy swapper, which will never swap a page into memory unless page will be needed. That means if some page is not required, it will not be fetched into the memory. Okay. See, there is advantage also, there is disadvantage also. So for example, whenever I need that page, and now if you are fetching at that time, maybe you need to wait for that. So early fetching is not there. So lazy swapper, what it does is, now anyways, this lazy swapper is related to the swap device and main memory. Okay, but again, swap device is nothing but your disk. Like in case of Linux, we have a separate partition called as a swap. Okay. So swapper that deals with pages is called as a pager. Just different names are there. Swapper is more generic. So swap in and swap out. If you are doing with each and every segment or with each or every page, because we studied both the memory management strategies, one with segmentation deals with variable sized blocks. That is what segments, like each and every segment is of not same size. Anyways, we already discussed the advantages and disadvantages of that, and then we came to something called as a paging. Okay. Now, if the swapper process that only deals with the pages is called as a pager, that's it. So pager like page out, page in kind of operations will be implemented there. Okay. Now the basic concepts for these are, what happens with swapping is pager guesses which pages will be used before swapping out again. Now how to decide on that? How to decide on that? Okay. So for example, looking at the nature of the program, say for example, let me give very simple example. Suppose you are writing a C or C++ program wherein global variables are there. Now global variables can be accessed from any function. It could be say main function or whatever number of functions are there. So there are more probability of those pages who store the global data from different parts of your program, right? So making use of those pages will have more probability. So swapper or pager will guess like that before swapping out again. Instead, what pager does is it brings in only those pages into the memory. That means whatever the pages that are required to start the execution. See, you may wonder if at a time if the processor executes only single instruction, maybe you think like one page is sufficient, but that is not the case, because even though you have a single instruction, maybe it is referring different addresses. In short, say for example, if I have done something like a is equal to a plus 1 or just a plus plus. Okay, now where a is stored, that data and whatever this increment instruction, that is a text, they may be at two different locations. So it is not always only single, but whatever the page is required, that must be taken into the main memory. Okay. How to determine then the set of pages that are required? For that, we need to add the functionality. I'll see there are multiple algorithms are there. Anyways, we'll go through different algorithms used for that. If pages needed are already in the memory, then there is absolutely no difference between the demand paging and non-demand paging. Because in non-demand paging, complete process is in memory. And say for example, let's give me a simple example. Suppose 25 pages are required for a particular process, and operating system has allocated something like 6 pages for each and every process. Minimum 6 pages, for example. So if 6 pages are there, now 6 pages will be loaded into the main memory. Maybe first 6 or whatever, depending upon the algorithm we have selected. Okay. Now the logical address will be converted to the physical address, and then we found out the frame, and that frame is already in the main memory, right? If that is the case, there is absolutely no difference between demand paging and non-demand paging. But if that page is not in the main memory, then we need to detect and load the page into the memory from storage. And while doing so, we need to take care of two things. Yes, you can load the page into the main memory from storage without changing the behavior of program and without needing to change the code by the programmer. That is the importance of this virtual memory. Page table. Till now, we saw the page table with just frame numbers, where page number is used as an index. Now in this diagram also the same concept is there. In addition to that, valid, invalid bit. So whenever V is there, meaning of that is whatever the required page is in memory, that is memory resident, and whenever I is there, that means that is not in memory. Okay. So for that, like for example, for any particular process, if you want to refer to page number 3, it will check at the third entry at the page table what is the frame number, and just in front of that it will check whether it is valid or invalid. If it is valid, it will directly refer the instruction. That means logical address is converted to physical address and it will refer the instruction. But if this is invalid bit, that means you need to locate and load that page. Okay, that process is also given here. That process also we'll see. Have a look at this example. Suppose there is one process for which 8 pages are required. So the size of page table is 8. All 8 pages are available on the disk, that is on storage. They are named as A, B, C, D, E, F, G, H. You can check it here. Let me highlight it. So for example, these are the pages available on the storage. Okay. This is the logical memory. And because of the concept of virtual memory, we can start executing this process without loading all 8 pages. So here you can check that page number 0, that is loaded, page number 2 is loaded, and page number 5 is loaded. Okay, so page number 0 from logical memory, it is A, loaded at frame number 4. So page table entry says, very first entry, you can check it here, page number 0, frame number 4, and this valid bit is this one. Okay, why it is so? Because that is loaded. Now page number 1, which is the B, is not available in the physical memory. So here you could have any garbage, no problem. But this valid invalid bit says that it is I. That means it is invalid page. And meaning of this invalid page is what? It is not loaded into the main memory. Okay. Now whenever you are referring to any address from page number 1, it will consult the page table. It will find that it is having invalid bit. That means page is not in physical memory. Such a situation is called as page fault. The word for that is page fault. Okay. So if there is a reference to any page, maybe first reference to that page will trap to operating system. Trap is like non-maskable enter. Meaning of that is very, very simple. You are trying to access the instruction or data, whatever it is. So first reference. Why first reference? Because that is the first instruction or data from that page which you want to access. That means now here comes the demand for that page. That is what the demand is, right? So that this first reference to that page will fail. Why it will fail? That is a page fault. That page is not available there. So this will be conveyed to operating system by sending some sort of trap interrupt to operating system. Okay. So this is called as page fault. Anyways, we will see what are different steps to handle the page fault. But whenever this page fault occurs, what are the things you need to do? Very simple thing, because processor cannot access anything directly from disk, that particular thing should be loaded into the menu. Okay. So very simple thing, the pages are loaded into the frames. That means operating system first of all need to find the free frame. Then take that page from disk to the frame. That means some sort of copy operation is required. So now the data from disk will be copied into the frame. So for that, the swapper or the pager, that process will schedule some sort of disk operation. Once it is loaded, the valid invalid bit is updated. So previously it was I, that is invalid, it will be changed to, and then that caused the page fault, because that instruction has to be restarted. That is actually some sort of wastage, especially whenever we have more than 2 bytes of instruction. There are something like 3-byte instruction. You can imagine something like in case of Intel Exchange, XEFG. Okay, so 3-byte. There are 3-byte instructions where first instruction is there, then one address is there, and then that is also loaded. No problem. But third byte is not available. So that results into page fault. So complete instruction has to be restarted. Okay. Now there are 6 steps required for handling the page fault. So let us start from, suppose there is one instruction called as load M. This is the instruction from my program. Load M, that means we want to load some sort of memory location into the accumulator. Now load M will try to reference the location EM, and whatever this EM address is there, remember that is logical address. Now this logical address needs, for that it will refer to the page table. So now this is the page table. Okay. Now this instruction is definitely coming from one of the page, and valid invalid bit of that is set to I. And meaning of this I is what? Page is invalid. That means page is not in main memory. If that is so, memory management unit will send some sort of trap interrupt to operating system. This is step number 2. So step number 1 is refer the logical address. For that it will consult the page table. From that it will found that the flag is set to I, that means invalid, page is not in memory. Memory management unit will send trap interrupt to operating system. Right. So step number 3 is now operating system will locate the page in the backing store. So for example, that page is available here on the backing store. Okay, so that is step number 3. Now this page has to be loaded. So that is step number 4. And again for that you need to find out the free frame. So find the free frame and then bring in the missing page. Now my question is, if there is no free frame available, what to do? Then few more steps are required, and those steps are, you need to select the victim process and few pages of that process must be swapped out in order to create the free frame. Assume that now the free frame is already available, so whatever this missing page will be taken from backing store, that is your disk, into the memory. Okay. Then we need to reset the page table. Reset the page table means whatever this I flag was there, we need to change it to V, and here we need to put the frame number. Okay. Now we need to restart this instruction. That is step number 6. So this time load M. Again it will refer. Now this time we will have it as a valid address. It will refer the physical memory, and that instruction will be executed. These are the steps for handling the page fault. Any doubt in this? Any doubt in this? Okay, 81 participants are there. Any doubt? So very first thing is what is demand paging, then what is page fault, then what are the steps in handling the page fault. Any doubt in this? Shall we continue? Okay. So let us move to the next slide. What are the aspects of demand paging? Okay. So the extreme case will say we'll start the process with no pages in memory. So just process control block will be available there. Not a single page will be loaded into the memory. So operating system will set instruction pointer to the first instruction of process, which is non-memory resident. That means that page also is not there in the main memory. That results in page fault. And for every other process, whatever the pages are there on very first access, that results in page fault. This scheme is called as pure demand paging. It is not just demand paging, because now see what happens in paging. All pages must be loaded into the memory. What happens in case of demand paging? Few pages can be loaded into the memory. Few, I am saying, not all. That is what the demand paging is there. What is pure demand paging? Do not load any page in order to start the process. So very first instruction will result in page fault, and from that onward, first access to every page results into page fault. So this is called as a pure demand paging. Okay. Now, like as I mentioned, given instruction could access multiple pages. So maybe single instruction will result in multiple page faults. For that, I just mentioned this instruction XCHG exchange, where content of memory address A, B. Now XCHG is instruction. So this is coming from text region, code segment. Now this is one address. Maybe it is coming from some other page, and this is one more separate address. So 3 bytes may be coming from 3 different pages. So even though this is a single instruction, it may result in multiple page faults. Okay. And for that, we need to see the locality of reference. Anyways, we'll see one example for this. Okay. So what is the hardware support needed for this demand paging? Yes, we need some sort of page table with one additional bit called as a valid invalid bit. And second memory is required, that is a swap device is required. Why it is required? Because whenever you select the process, every time it will not load from the disk, but it will load from some fast disk, something called as a swap access. And at a hardware level, we need to some sort of instruction restart. Let us see the instruction restart in the next slide. So this is the instruction restart. So that could access several different locations. For example, moving block, maybe auto increment decrement location. In that case, restart, we need to restart the whole operation. And that typically creates a problem. For example, whenever it results in some sort of source and destination address overlap. Something like I want to move the block of 20 bytes from address 100 to 110. So it is size of something like 20 bytes, and I want to shift it by 10. Whenever I want to shift it by 10, that means already we have some sort of data there. This is called as the overlapping of the addresses. Okay. You imagine something like you have an Excel sheet in which you have assume one column is there, say C column is there, and there are a few contents in say C5, C6, C7, C8, C9, something like that, C9, C6. And now I want to move these contents from C5 to C7, complete block. Assume 10 cells are there, which we want to move from C5 to C10. But C10 already has some sort of data, no? Okay, so that has to be managed by the operating system, especially whenever source and destination addresses overlap with each other. Now we need to see the performance of this demand paging, or maybe in case of worst case. Now whatever we discussed, all those steps are there. Now see performance of pure demand paging. Very first thing is a trap to operating system. Why trap? Because whatever the desired page is there is not in the main memory, it results in page fault, and page fault sends trap signal or trap interrupt to the operating system. Do you know what is trap? It is interrupt, and each and every interrupt will have their own interrupt service routine, ISR. So you are actually executing in user space. Now you are moving to the kernel space, because all these interrupt service routines, even your system calls, are implemented as a privileged part in the kernel. That is what the kernel space is there. So that means you now need to switch from user space to kernel space for that. Whatever the user registers are there, whatever state of process is there, context switching steps we studied already, right? So we need to save the user registers and process steps somewhere. Next, when interrupt is sent to operating system has to find out what is the reason behind that interrupt. That means OS need to determine that the interrupt was a page fault. That is stage number 3. Next, it has to check whether that page reference was legal and determine the location of page on the disk. See, first thing is legal. That means if that process has the 10 pages and whatever the page referred is a part of logical address space of that process, then and then only we call it as a legal page, right? So first of all, OS need to see if that access is legal. It is really part of address space and part of other process. Okay, so that is stage number 4. Next, if it is legal, you need to find out location on the disk. Whatever your backing store is there, whatever your swap space is there, find out that page on the swap. Then issue read from disk to free frame. That means such a process, because now here disk IO is used, your process should wait in a queue for this device until the read request is serviced. Okay. So because see, we want to copy something from disk to memory. So disk is slow, right? So some sort of waiting time, seek latency time is required there. Then it will begin the transfer of the page to a free frame. Now while waiting, for step number 5, allocate the CPU to some other user, because we want to utilize the processor. Send the interrupt from disk IO subsystem. Meaning of that is whatever the desired page that is on the backing store loaded into the main memory. Okay, so it will send interrupt. So again, save the register and process state for that other process, because in stage number 6 we have scheduled some other process. No. Okay, so once the disk IO is completed for my process, again that other processes registers and process state will be stored. So again, that is the concept of context switching. Next, we need to determine the interrupt was from the disk. That is stage number 9. Stage number 10 is correct the page table. Previously the flag was I, that is invalid. Now we need to modify it to V. That means now the page is valid. Wait for the CPU to be allocated to this process again. That means now we are waiting for a schedule, so it is in the ready queue. So I need to wait for the scheduler so that my process will be scheduled. Okay, and once my process is scheduled, we'll restore the user register and process state with new page table and resume the interrupted instruction. So even though we are simply saying just a page fault, these many stages are there in case of worst case. So that talks about the performance of demand paging. So 3 major activities are there in this: providing service to the interrupt, reading the page, for which lots of time is required because disk IO is involved in that, and restarting the process. Even though small amount of time is required, definitely some sort of context switching time is involved in that. This page fault rate, assuming it is P, the effective access time is given as 1 minus P multiplied by memory access time. So now memory access time, it is 1 minus P time, that is what the probability. If P is equal to 0, it is just memory access time. Okay, saying that are in the main memory. If P is equal to 1, that's the case where every reference is a fault. In that case, it is P multiplied by, now swap page out, time required for that, swap page in, time required for that, and whatever the page fault already is there. So that is what the effective access time for. And this is just one example of that. So for example, assuming that memory access time is just 200 nanoseconds and average page fault service time is 8 milliseconds, putting all these value in the formula, it is 1 minus P times 200, that is the memory access time, plus P into 8 milliseconds, which is the average page fault service time. Now, if one access out of 1000 causes a page fault, assuming that the size of my page or frame is say 1000, so the first instruction will result in page fault. Remaining 999 pages already there in the main memory. Okay. So this will definitely slow down the factor by 40. There are few demand paging optimizations are also there. That will continue in the next lecture. For now, we'll stop here.